Dear student, I hope you are fine and doing well. Today, our lecture is about Gram-Schmidt Orthonormalization. It's one of the quite important procedure to convert any basis of vector space or inner product space onto a orthogonal as well as orthonormal basis. So today we will discuss the what does Gram-Schmidt procedure is actually. So let us start with some basics. So the contents of today's lecture is orthogonal vectors, orthonormal vectors, and Gram-Schmidt process. Let us start with some basic definition that we have seen in our earlier classes that two vectors are orthogonal if and only if their dot product is zero. Let us say if you have more than two vectors and we can say they are mutually orthogonal. In that case, in the pair of vectors is orthogonal if vi into vj is zero for all ij not equal. It means that is vi in dot product of vi and vj vectors. These are basically from this set are equal to zero if I and j are not equal. Let us check these three vectors from R3 orthogonal or not. Let us take their mutual orthogonality. Let v1 and v2. Let's say let me on this. Spot like this one. V1 and V2, the dot product is zero. Then V2 and V3, it's also zero. Then V3 and V2, it's also zero. In that case, we can say these vectors, or the set of vectors are mutually orthogonal, or we can say these are orthogonal. Let us say another example. Uh, so we will what you call we just take what you call generalize the concept of orthogonality and orthonormal towards vectors. If you have sets, let say some set S of vector in a vector space. Let me check this one. Like this, this is a set of vector in a vector space like this one. In a vector space, V is called orthogonal, called an orthogonal set if every pair of vector is orthogonal. Let us say S is a subset of V, then dot product of Vi into Vj is zero for all I and j are not equal. So orthonormal set is basically when I and j is equal, then in that case their dot product is 1, and when I and j are not equal, then their dot product is 0. If that set, any vector in this set satisfy these two properties, then in that case we can say these are orthogonal and sorry, orthonormal basis. There is a very good result that if S is a basis, that is a vector in S are linearly independent as well as they are uh, linearly independent as well as spanning the whole set S. In that case, the S is called orthogonal or orthonormal basis. If S is consist of basis element. So let us take one non-standard orthonormalization for R3. It should be R3. So we take three vectors in R3 is consist of set S, V1, V2, V3. So we take first of all mutual check mutual orthogonality. Uh, so V1, V2, V1, V3, and V2 and V3. Their dot product is zero, and if you take its dot product with itself, then there will be 1. And if you can see over here, the dot product with itself, it means I into I. V1 into V1, it is means to say its dot product with itself is 1. and dot product other than itself is zero. In that case, these vector will be, which is in set S, will be uh, orthogonal base, orthogonal vectors, orthogonal set or orthogonal base. So in that case, if you can see, if we take dot product with not itself but other than with other vectors in set S, their dot product is zero. But if you take dot product with itself, it means length of this vector is one. In that case, the set S is orthonormal set. So let us take another example of P3. It means polynomial consists of what you call it. P3 is a set of polynomial whose degree is 2 or less than 2. In that case, if we can say the dot, the coefficient P and Q are element of this P3. In that case, the dot product is the dot product of the corresponding coefficient of this polynomial. P3 is the second degree polynomial and Q3 is also second degree polynomial. In that case, we define the dot product between their coefficient are like that. The standard basis in that case, in case of P3, are 1x and x squared. To show these are orthonormal, let V1 can be written as 1 plus 0 in x plus 0 into x squared, and V2 can be written as 0 plus 1 times x plus 0 into x squared, and V3 0 0 into 1 into x. So we take dot product of V1 with V2. So their coefficient like this one, we define this. We take this polynomial and define the dot product with this inner product space. Like the dot product V1 and V2, we have to multiply its corresponding coefficient like V1, V2. So their coefficient is V1 0, then their coefficient is 0 into 1, like this one, and then 0 into 0. In that case, you can see over here all are 0. If you can take V1 and V3, V1 and V3, we have to multiply the coefficient of corresponding coefficient of polynomial in V1 and V3. 1 into 0, 1 into 0, 0 into 0, then 0 into 1. In that case, it is also 0. If you can take the norm of each vector, in that case, the norm is 1. In that case, both properties are not satisfied for this basis element of P3x. In that case, we can say this basis, which is this one, standard basis of P3x, is orthonormal. Dear student, this is one of the very fundamental result. If you have some set S is an orthogonal set of non-zero vector in an inner product space or vector space, then S is always linearly independent. Basically, orthogonality ensure the linearly independence. If V is a any vector space or inner product space, so you just keep this V is a vector space of dimension n, then any orthogonal set of n non-zero vector is a basis for V. Dear student, this is one of the fundamental results to check whether some vectors, if these vectors are orthogonal, then either they form basis for V or not. In last classes, we have test basis of any vector, either it form basis for any vector space or not. We have to check these two properties. First of all, we have to check either these vectors are linearly independent, and second what that vectors are spanning the basically through any subset that we can span the whole vector space S. So we have to check two properties in our previous classes. But that corollary of this theorem, this is the corollary of this theorem, that give another idea how you can say this. Either if you have uh, that basically ensure if you have set of orthogonal vector, it shows that these will always form a basis for vector space V. Let us say to show that these are form a basis for R4 or not. So these are four vectors from R4. It consists of the set S containing the four vectors from R4, and this is a subset of R4. To check either these are form a basis for R4 or not, so we have to check its orthogonality. So V1 and V2, V2 and V1 and V3, V1 and V4, then V2 and V3, V2 and V4, V3 and V4. All these are their dot product is zero. It reflects that S is orthogonal. In that case, S form a basis for R4 from previous 4L. So, dear student, this is another interesting result. If your set is orthogonal, so it will always form a basis for any vector space V. So, in here, the vector space is R4. So, the theme of basically, if I can say, the today our class is fundamentally is just to uh, just about Gram-Schmidt process. What is the theme of Gram-Schmidt procedures? If you have, say, independent vectors, say A, B, C. So you what these procedure, if you apply Gram-Schmidt procedure to any linearly independent set of factors, that convert your independent set of factor into a orthogonal as well as orthonormal vectors. This is the basically the idea of Gram-Schmidt procedure. And fundamentally, why we need Gram-Schmidt process? Because in diagonalization and in case of you can say singular value decomposition, we have basically need two types of what you call the matrices. One is orthogonal and another one is orthonormal. So in that case, we have to we must know about how to transform any matrix or how you can transform any column or row of any matrix into a orthogonal or orthonormal set of vectors. In that case, the matrix will be orthogonal or orthonormal matrix. So the procedure, if you want to turn orthonormal basis or orthogonal basis, uh, if you have any basis like and you want to change it to into orthogonal or orthonormal basis, you need to use Gram-Schmidt process. So let us define, let us start what is actually Gram-Schmidt process. So dear student, if you have basis of any vector space V, like this is a basis for any vector space V. So let V is, you suppose V equal to V1 and V2 is V2 minus projection of U2 over V, W1. It can be written as U1 minus projection of what you call the uh, U2 over W1. In that case, the dot product of U2 with V1 and dot product of V1 with V1 into V1. That is in the direction of V1. Similarly, we did for V3 and Vn. So ultimately, these are V1, V2, V3 up to Vn are orthogonal basis, and V double dash. If you can divide V1, V2 up to Vn with its norm, we will get orthonormal basis. Let us understand this procedure with the help of one or two examples. Like if you have three element in basis of R3, let's suppose V1 is first factor and V2 is V2 minus V2 dot V1 divided by V1 dot V1 into V1. So V2 is this one, then the dot product of V2 with V1 is 3 and dot product of V1 with V1 is 2, and then multiply this with V1 vector V1 like this one. So in that case, you will get uh, V2, and similarly you will get V3. Apply the same procedure. In that case, you have three vectors in standard basis, and orthonormal basis also consists of three vectors, like V1, V1, V2, and V3. Here the basis, standard basis that which are not orthogonal are U1, U2, U3. So B dash is the orthonormal basis. So this is V1, V2, and V3. We put it over here. So orthonormal basis are basically, if you can divide this with its norm, you will get orthonormal basis. If you can multiply it with itself, you will get one. If you get multiply this vector with this one individually, you will get zero. In that case, you will see these are orthonormal bases. Let us find orthonormal basis for the solution space of homogeneous system. First of all, you have to solve it with Gram-Schmidt Gauss-Jordan elimination. And in that case, if you can see over here, we have two free variables, and we have two vectors, and these are basically the solution of this homogeneous equation: minus 1 2 1 0, and this 1 minus 8 0 1. In that case, we have basically the basis for the solution space are v1 and v2, which is minus 1 2 1 0, and this one. So you will have to calculate this. Sorry, you can say u1. I just write it mistakenly. I have written v1, v2. It must be u1 and u2. So v1 is u1. This one, like u1, and v2 is u2 minus u2 dot v1, like this one. This is my u2. So you just correct it like this one. It should not be like this. So V2 is V2 minus dot product of U2 with V1, and V1 with V1 with V1. So in that case, the dot product of V1 with V1 is 9. So in that case, the student, ultimately we have like two bases, and corresponding we have uh, the basis set of orthogonal bases are also cardinality of this orthogonal bases are also two. In that case, cardinality, I mean to say number of element in orthogonal basis. Similarly, if you divide this set each and every element of this vector with its norm, so in that case we will get orthonormal basis. Dear student, today this is our class about Gram-Schmidt procedure. I hope you understand. And if you have any question regarding orthogonalization or Gram-Schmidt procedure, do ask me. Till then, thank you all, and please stay at home. May Allah bless you all. Allah.